Hello, everyone, and welcome to our big questions in Muon g-2 special Snowmass Colloquium. We are very excited to have this colloquium on a very high-profile result. We just heard in a separate meeting that it had a media reach of 7.5 billion people, if I remember correctly. I'm not exactly sure what that means or how it compares with other high-profile physics results. But it is certainly one of the most exciting recent results in our field, and we are very excited to welcome our speakers today. So I'm delighted to introduce our first speaker, Dominic Stöckinger. He earned his PhD from Karlsruhe, studying higher order calculations in supersymmetric models and renormalization theory. Since 2008, he is a professor for elementary particle theory and phenomenology at Technical University Dresden, where he is currently the director of the Institute of Nuclear and Particle Physics. He has been working in the Fermilab g-2 effort from the beginning. He was among the organizers of the seminal 2007 Glasgow topical workshop on Muon g-2. He is among the authors of the 2020 white paper that gives the anomalous magnetic moment of the muon in the standard model. And he has written one of the most authoritative papers on potential new physics explanations in light of the recent Fermilab measurement. And we're also excited to welcome from the experimental side, Brendan Keyberg. Brendan did his PhD at the University of Illinois, studying muon capture on the proton at PSI. He then became involved in the Muon g-2 experiment and joined Fermilab, first as a Lederman Fellow and then as a Wilson Fellow. He was instrumental in the effort to shim the magnetic field of the experiment to high uniformity. He heroically led the experiment through the very challenging run one period where the result comes from, and he is currently leading the magnetic field analysis. And he was also part of the Snowmass Young Physicists group during the 2013 Snowmass process. So we are extremely fortunate to hear today from both Dominic and Brendan. I invite you to submit questions in the chat through the talks. We will pick them up, potentially having a discussion as this is a colloquium, and there will be dedicated times through the event for question and discussion where you're welcome to raise your hand also. So with that, Dominic, you can start the presentation.
Thank you very much. Can you hear me now?
We can hear you very well.
Okay, excellent. Thank you very much for the invitation and for the possibility to give a talk in this nice series of Snowmass colloquia on big questions. And today the topic is Muon g-2, as you heard. It was really a spectacular result that appeared this April, the first measurement of run one of the Fermilab g-2 experiment. So in my talk, I will discuss theory, both in the standard model and from the point of view of physics beyond the standard model. And the talk is grouped in these three parts. I will begin with a brief motivation and some definition of g-2, then discuss the standard model situation, and finally turn to physics beyond the standard model, which is motivated because of this discrepancy that we have right now between the standard model and the experimental measurement. And in that section, I will give some general remarks, some examples, but also I will discuss the relationships that we can identify between g-2 and maybe some big questions that we have in fundamental physics right now. So fundamental physics and research on fundamental physics can often be organized according to the frontiers. That is also the way Snowmass is organized. There is the high energy frontier with the LHC and future colliders like E+, E-, or even muon colliders. There is precision frontier, rare processes, neutrino physics, and g-2 of course belongs to the precision frontier, but also flavor physics, dark sector searches is also part of rare processes and related to g-2 in that sense. There is the cosmic frontier where dark matter searches belong, or dark energy research. So there is a very broad program to investigate deep open questions, and in this talk we will discuss a little bit how g-2 fits into this very big picture. Let's begin with the standard model of particle physics, which is actually an old theory. It has been established around 50 years ago. The standard model describes all known particles and forces, the quarks, the leptons, the spin 1 particles, WZ, photon, and gluon, and also the spin 0 Higgs boson. And g-2 of the muon is actually this very special quantity which is sensitive to all particles and all forces that we know via quantum fluctuations, as we will see in a moment, which is very important. And so we can really test our full understanding of particle physics with one single number, which is really nice. But I also want to stress that the standard model is not like a periodic table where we list only the particles. It is a very, very deep, really predictive quantum field theory, which has very fundamental properties. And so it's a relativistic quantum field theory, which is based on the marriage between quantum mechanics and relativity, and therefore predicts antiparticles, creation and annihilation processes, local interactions that are described by Feynman diagrams, and so on. It uses the concept of gauge invariance, which implies very specific interactions and relationships of interactions of the spin 1 particles. And the standard model builds on electroweak symmetry breaking with a Higgs vacuum expectation value, which again implies relationships between masses and interactions. And all these deep predictions coming from fundamental principles are all experimentally tested and very, very well confirmed. And so testing the standard model further is, of course, extremely crucial. And in spite of this fantastic success, there are deep open questions as well. And one well-known is, of course, the mystery of dark matter. We know or have strong evidence for the existence of dark matter in the universe, but it doesn't fit into the standard model. Therefore, we want to know what it is, and we need experimental clues for it. And maybe g-2 can be related to dark matter. Furthermore, there are mysteries like what is the origin of the Higgs field or of the electroweak Higgs potential and electroweak symmetry breaking? What is the origin of the generations of quarks and leptons and of their Yukawa interactions with the Higgs boson? And again, actually, these questions here might be related to g-2, and we could make progress by investigating g-2 as well. Let me define g-2 now. G itself is, of course, a quantity that measures the magnetic dipole moment of the muon in certain natural units. And the normalization is such that if you put a particle into a homogeneous magnetic field, like the muon, then it performs, first of all, an orbital motion, and the frequency associated is given by some factor times 2. On the other hand, the spin performs a precession, and the frequency is given by the same factor times g. So that means g-2 or g equal to 2 is special. So you see it here on the right. So if you put the particle into a beam on an orbit and you happen to align the spin at the beginning perfectly with the momentum, and g were exactly equal to 2, then the alignment would remain forever. But if g is bigger than 2, like for the muon, then slowly the spin deviates, and there is a relative rotation between the spin axis and the momentum axis. And the experiment is directly sensitive to this relative rotation, to this frequency omega a, which is proportional to g-2 or a mu, which is g-2 over 2. In quantum field theory, g-2 is described by such Feynman diagrams where the muon interacts with a photon field via loops. And such Feynman diagrams can be computed and actually related or rewritten as a so-called effective Lagrangian, which is written here. And the effective Lagrangian contains psi bar psi for the muon, connected with a sigma mu nu matrix that describes the muon spin, essentially. And this is then multiplied with the F mu nu field strength tensor for the electromagnetic field. And so in that sense, you see that this effective Lagrangian really corresponds to a magnetic dipole moment proportional to the spin. And so with suitable normalization, this coefficient in the effective Lagrangian is directly g-2 or a mu. So in some sense, it's a simple quantity, both experimentally and theoretically, which means that we can calculate and measure it to 10 to the minus 10 level. But at this level, nothing is simple anymore, obviously. So let me come to the standard model prediction. And at the top, you see the current value proposed by the theory initiative for the standard model value. And it has this precision of 4 times 10 to the minus 10. And this number is based on a number of workshops, and it is defined in a white paper from last summer with more than 100 authors. And actually, it's a snapshot, a current snapshot. But overall, this is an ongoing effort to further and further improve the standard model prediction in this theory initiative. So let me just give you some highlights of this. First of all, it's an extremely difficult calculation to get to this precision, and it's a playground for quantum field theory. So if you're interested in quantum field theory, this is a nice playground for you. Many different interesting and complicated methods need to be applied to get to this number. Then all particles of the standard model contribute, as I mentioned already before. So even the heaviest particles that we know, the W, the Z, the Higgs, and the top quark, they all contribute. They contribute via the so-called weak interaction contributions, and they amount to 15 times 10 to the minus 10. So it's small, but relevant at the current level of precision. And then let me highlight that maybe you know that the largest uncertainty right now in the theory prediction comes from the hadronic contributions, in particular from the so-called hadronic vacuum polarization contributions, which are given by these diagrams here, where a photon is connected to a hadronic blob. And this is at the moment the critical issue to improve further. And let me just describe briefly what the status is. So traditionally, this is evaluated using an exact quantum field theory dispersion relation, which comes from unitarity and causality of the S matrix, so some deep principles. And this allows to relate the Feynman diagram that we want to experimental data coming from scattering, E plus E minus scattering to hadrons in the final state. So the more precise we know this experimental data, the more precise we can translate it into the hadronic vacuum polarization contributions. So this is the traditional way that this is done, and the current theory initiative prediction is based on the compilation, conservative combination of several of these most up-to-date predictions of this kind that you see in the gray rectangle over there. But in this plot, you also see, and maybe you know already, that there is a second method coming along, namely lattice gauge theory, lattice QCD, another non-perturbative technique, which is making rapid progress. But it was not yet at the necessary level of accuracy at the time of the theory initiative white paper, as you see in this cloud of blue points here with the error bars. However, there is a quite recent single, quite precise lattice result from the so-called BMW collaboration, which is the second point in this list. And its uncertainty is almost as small as the one of the dispersion relation-based results. And this is not yet used, but it will for sure be taken into account in the future. But what this illustrates is that the standard model prediction is work in progress, and there is at the moment a lot of effort going on in scrutinizing and further improving the different lattice results. And for sure, many of these lattice groups that you see here will come up with more precise results in the near future. So currently, the status is this. The standard model prediction here based on the theory white paper is given by the bar on the left, and the experiment will be described by Brendan later. And there is right now a 4.2 sigma discrepancy, or in absolute terms, we have a discrepancy of 25 times 10 to the minus 10. And that brings us to physics beyond the standard model. So let me come to this here. So zooming out a little bit, what we need to explain now, if we take it at face value, is a deviation of 25 plus minus 6 times 10 to the minus 10. The question is, how can one explain this number in physics beyond the standard model? And the first very simple but important remark I want to make is that it's actually a large deviation, even though it might sound small to you, but you have to compare it to the standard model weak effects, which were 15 times 10 to the minus 10. So 25 times 10 to the minus 10 is almost twice as large as the standard model weak contributions, but generally we expect that new physics contributions are suppressed by heavy masses, and therefore it's not obviously easy or even possible at all to explain this deviation by any new physics model, because you know that in many other experiments there is even a per mil accuracy agreement between electroweak observables in experiment and in the standard model prediction. So how can we have such a per mil level agreement in many observables, but in G-2 we need a 100% effect from new physics? How is this possible? And how it can be possible, you can kind of understand if you look at this list of 4 quite important and distinctive properties of G-2. So G-2 is loop induced, it is CP and flavor conserving, and it is a chirality flipping quantity. Chirality flipping means that the Feynman diagrams connect the left and the right-handed muon by necessity. And so all of these properties make it different from many other tests of the standard model. Loop induced makes it complementary to collider observables. CP and flavor conserving makes it different from, for example, electric dipole moment measurements or B2S gamma or mu2e gamma measurements. And the chirality flips make G-2 very different from other electroweak precision observables where we have this agreement between the standard model and experiment. So this list should tell you that if you want to explain in your physics this large deviation of 25 times 10 to the minus 10, then you need to go to special models, special scenarios for physics beyond the standard model, where you kind of maximize these differences and maximize these complementarities. And even in those special models, you might need to go to specific regions in parameter space where the difference between CP violating and CP conserving observables is made use of. And so let me just see how I'm doing with time. Okay, so let me now come to the relationships to some deep questions. And actually, the list that I had before really points to 2 particularly promising connections between G-2 and some of those big open questions that we are having. And so the first connection, which one can identify, is the connection to dark matter or to dark sectors, either heavy or light dark sectors. So dark matter particles or dark sector particles in general are by definition hard to see in detectors because they don't interact with visible standard model particles like electrons or with quarks. Okay, but dark matter particles could couple to the muon, and then via loop Feynman diagrams, they could contribute to G-2. And so indeed, it's easily possible in a variety of concrete scenarios that dark matter particles or dark sector particles could contribute to muon G-2 and explain this deviation. So conversely speaking, by measuring G-2 precisely, we can learn something about how dark matter might be realized or how it might not be realized. So just some concrete examples for that. For a long time, one interesting candidate was dark photons. Dark photons are basically copies of the normal photons with essentially the same interaction, just multiplied with a very small prefactor. And those dark photons were proposed as a viable and also quite appealing explanation of the previous deviation of G-2 after the Brookhaven experiment. But then many experiments came along and basically ruled out entirely the explanation of G-2 by dark photons. So that also means that those models that you need to propose, you have to go to specific parameter spaces, parameter regions, and they can be tested by other experiments. And here in the case of the dark photon, the tests have led to a complete exclusion of the scenario. On the other hand, there are viable scenarios remaining. For example, you can have a Z prime, a new gauge boson, with a U1 gauge group, a very simple kind of new gauge boson, which couples only to muons and to tau leptons with a so-called quantum number L mu minus L tau. So this new gauge boson cannot couple to quarks, it cannot couple to electrons, therefore basically at colliders it cannot be produced easily. So it's essentially invisible, but it could couple to muons, and then it can explain G-2 via these loop Feynman diagrams. And the plot on the right is a current status of this model against G-2. And you see, again, it is cornered by many different experiments which already rule out a lot of its parameter space. However, there is a certain parameter space remaining. And in this space, the mass of this Z prime boson is between 10 and 100 MeV, so an interesting mass range for light new particle searches. So the general situation is that you can explain G-2 in a variety of such models. And in each of those cases, other experiments might be able to test and constrain the parameter space, which is relevant for G-2. So this is the first connection. The second connection is that G-2 can provide a window to the muon mass generation mechanism. By this, I mean it can provide a window to the Higgs sector and also to the Yukawa sector by which fermions get their mass. So for the quantum field theorists among you, let me write down the appropriate equation. So what I mean technically is that the quantum field theory operators for the muon mass and for G-2 have very simple similar properties. Both are chirality flipping. And in the electroweak standard model, both are actually not gauge invariant, and you need a Higgs mechanism to make them gauge invariant. So therefore, both observables are strongly connected. So in more pictorial terms, remember that G-2 basically corresponds to this relative rotation of the spin axis compared to the momentum axis. And such a continuous spin rotation is only possible for particles which have a rest mass and a rest frame. And so this gives the relationship between G-2 and the rest mass of particles. So particle without a rest mass, like the photon, cannot have G-2. So there the spin can either point forward or backward, but it cannot have an angle compared to the momentum. So you have this relationship to the muon mass, but the muon mass in the standard model arises in this very complicated and mysterious way. First, you need a Higgs field, then a Higgs potential with a Mexican head structure. The Higgs needs to condense in the vacuum, and then via Yukawa couplings, the muons couple to this Higgs vacuum expectation value, and thereby the muons receive their mass. And so there are obviously many, many open questions associated to this picture, and many new physics scenarios change the Higgs potential, change the Higgs sector, or change the Yukawa sector, or everything. And in all those models, G-2 can be strongly modified. And so those models can provide explanations of G-2. And conversely, again, we can learn about these models by measuring G-2. And so let me also give you some examples for that situation. One very well-known example is supersymmetry. In supersymmetry, you have an extended Higgs sector, you have an extended Yukawa sector, you have the super partners, Higksinos, muons, and you also have a dark matter candidate, so it ticks all the previous boxes. And via those enhanced Yukawa sectors and enhanced chirality flip, supersymmetry can easily explain G-2. And so, but again, supersymmetry is cornered by many observations and many experimental constraints. Dark matter produces constraints on the SUSY parameter space, LHC as well. Lepton flavor violating observables provide constraints, but actually it's not so difficult to find parameter regions which are actually quite natural, where supersymmetry is compatible with all constraints, can explain G-2 and the dark matter relic density at the same time while evading LHC constraints. Similarly, there is something called a 2 Higgs doublet model, where we have more Higgs bosons and again enhanced Yukawa sectors. Therefore, we change the muon mass generation mechanism, and again we get large enhanced contributions to G-2, which are again constrained by many experiments, again by LHC, but in this case also by tau lepton measurements, by B physics measurements, and again also by lepton flavor violation experiments. And the current situation there is that you really need to maximize all couplings that you have available in this model, maximize against all available constraints, and then you are just able to explain the current value of G-2. But that means once some of those experiments improve, you might either eliminate the explanation or really find evidence for it. Similarly, leptoquarks are interesting scenarios where you can explain G-2. They also amount to new Yukawa-like couplings where the muon couples to top quarks. In that case, they involve new flavor structures, and also they are strongly constrained by LHC and flavor observables. Okay, so let me conclude. The standard model prediction for G-2 is really an interesting and very, let's say, fascinating calculation. You need a lot of quantum field theory tricks, and it's really a playground for quantum field theorists as well. And there is the theory initiative, which is a worldwide and ongoing effort. And I stress here ongoing, since this is your opportunity also for young physicists to enter this field if you are interested in particular in these non-perturbative quantum field theory techniques. Regarding beyond the standard models, physics contributions, as I stressed, we need a large effect compared to the weak contributions. And in this way, we get connections to deep questions like dark matter and the origin of flavor or the origin of electroweak symmetry breaking. Many concrete models can explain G-2, but all of them are constrained significantly by existing other experiments. And so I highlight here a number of experimental tests which are therefore motivated. And again, this is an opportunity for the experimentalists among you. Higgs coupling measurements are important because they are also related to the muon mass generation mechanism. B physics measurements are important. Tau physics is important. Lepton flavor violation, electric dipole moment, light particle searches, and also future colliders would be very important to test G-2 explanations. Another remark I didn't stress at all, but you might be familiar with the so-called B physics anomalies. There, like in G-2, are some discrepancies between the standard model and experiment. And actually, you might like to explain those B physics results simultaneously with G-2. That does not seem to be easy. So this is also a chance for the model builders among you to come up with appealing, natural, or simple explanations of all of those observations at the same time. So I want to end with this. So there are many opportunities. It's an exciting field. That is just one of the Fermilab measurement, and the theory initiative is ongoing. So many opportunities for you and a lot of potential for future improved understanding of fundamental physics. Thank you very much for your attention.
Thank you very much, Dominic, for the excellent talk. Yeah, I'm seeing some people clapping. Takes some time to try to find the clapping response, but yeah, certainly applaud this presentation. It was excellent. We have a quick question in the chat, and the floor is open for questions. Let's take a few minutes for questions and discussion with Dominic before we go on and hear from Brendan, and we will have more time for general discussion at the end. So I think you addressed this, but there's a question. Why might dark matter interact with the G-2 of the muon? So could you go over a little bit again about how this might affect?
Yes. Of course, why we don't know, but of course there are viable and appealing models. For example, this scenario here, where we have this U1 with the so-called L mu minus L tau quantum number, is a good example of a model which is actually motivated not only because it can describe the G-2 result, but it also has some really deeper theory motivation, since you could investigate from a theory point of view, what are the possible gauge groups that you can write down which do not have the problem of the so-called gauge anomalies. And then there is just a small list of gauge groups that you can write down which do not have those anomalies, and this is one of the few. So this U1 L mu minus L tau is an appealing gauge group because it is just one of these few anomaly-free gauge groups that you can have. And therefore it's motivated to study it. And here in this model, L mu minus L tau means the lepton number of the muon minus the lepton number of the tau. So basically the gauge boson, the spin 1 particle that is predicted in this model, would couple to the muon with strength +1 in some units. and it couples to the tau electron with strength -1 in the same units, and it doesn't couple to anything else. So in that way, you would get Feynman diagrams which look essentially like the following Feynman diagram. Let me just try to find it here. So it would look like this Feynman diagram, but the weakly line here would be this new gauge boson which couples only to muons and taus. So this Feynman diagram would then just have a value which explains the 25 times 10 to the -10. And in order to have this value, you need a particular value of the mass and of the coupling strength of this new boson. And that was the plot that I showed you. If you are in this particular window for the masses between 10 and 100 MeV, and on the other axis, the coupling strength was shown with this appropriate value of the couplings, you get the correct value for g-2. Okay, maybe now I realize suddenly that I've kind of misinterpreted the question, because this Z prime is actually not on its own dark matter. So sorry for this. I was going in the wrong direction, but it's a dark sector particle, and dark sectors are, of course, maybe a bigger thing than dark matter, because dark matter motivates that maybe there is a variety of new particles which we don't see, and such as Z prime would be one of those dark sector particles, but on its own it would not form dark matter. So sorry for that. Supersymmetry would be an example of a dark matter particle which couples to muons, and then the lightest supersymmetric particle would be just one of those many SUSY partners of standard model particles, like SUSY partner of the photon. This automatically couples to the muon because the photon also couples to the muon. Therefore, its SUSY partner does it as well, and then you have a coupling of a dark matter particle to the muon. Sorry for this misunderstanding of the question, but I hope I could answer it a little bit anyway.
Excellent. Yeah, it's a great distinction too. What might address the dark matter. Jiamin, would you like to unmute and ask the question yourself?
Yeah, hi. My question is why there is no discrepancy for the g-2 as observed for the electron. And I wonder if the reason is because the QCD effects get suppressed there.
First of all, maybe you know that there used to be a slight discrepancy observed also in the g-2 for the electron. But at the moment, this discrepancy is kind of gone away. There are two different, let's say, in that case, the difficulty is not the hadronic contributions to the standard model. In the case of the g-2 of the electron, the critical issue are really the simple QED contributions, because those QED contributions are depending on the fine structure constant alpha, of course. And the limiting factor in g-2 of the electron is really how precisely do we actually know the fine structure constant alpha. And so therefore g-2 of the electron, and comparing it between standard model and experiment, depends on other measurements of the fine structure constant. And those measurements at the moment have there are two of them, and they do not quite agree. And therefore there is an uncertainty in the standard model prediction for g-2 of the electron because of this fine structure constant measurement. And what needs to happen there is we need a more accurate and let's say more unambiguous determination of this fine structure constant, and then we can also do the same comparison. However, let me mention one important difference, namely all these contributions of heavy particles, be it hadrons or new physics particles or W bosons or Z bosons, they are always suppressed by the square of the heavy masses, and therefore the ratio between the muon mass and the electron mass is very important. So the new physics and also hadronic contributions to the electron, they are 40,000 times less important than for the muon, because the electron to the muon mass ratio squared is 40,000. And that is why probably we do not see anything in the electron g-2 right now simply because any of those effects from heavy particles are so strongly suppressed by the small electron mass square that at the moment the sensitivity is just not high enough. So the muon g-2 is this basically perfect quantity. We can measure the muon precisely enough, not quite as precisely as the electron, but the relative precision compared to this muon mass square suppression is higher than for the electron. So in muon g-2, we have a higher sensitivity to new physics and heavy physics in general than for the electron.
Excellent. Thank you very much. Yeah, thank you very much for the excellent response. I see we have one more hand raised, but we are at the time that we need to move on for Brenton's scheduled part. But Gilvan, if I'm pronouncing this right, I guarantee we will have time to pick up your question at the discussion time after Brenton's talk. So thank you very much, Dominic, for the excellent presentation and discussion. Could you stop sharing? And thank you. Brenton.
I'm Nolas. Can you hear me?
Yes, we can hear you.
Okay, and my slides are displaying.
Looks very good.
Okay, excellent. All right, very good. Thank you very much. So I'm really delighted to have an opportunity to talk with you all today and talk about some of the big questions in Muon G-2. And in particular, I'm going to come at this from an experimental perspective. I'll try to define that perspective in a moment. So the outline of this talk, I'm just going to review sort of qualitatively how muons probe the universe, give a status update that motivates improved calculations and measurements. And then I'm going to talk about different places where experiments that are ongoing or ones that you could get involved in can actually give us additional insights into this discrepancy. And so I'll talk about the theory, and I'm really going to try to focus on the experimental inputs there. I'll talk about the experiment. I'll give a very brief recap of the recent effort, and then talk a little bit about the status and the outlook. And then I'll try to tie it together with some ongoing and future experimental efforts separate from the G-2 experiment. And throughout this talk, the question that, the simple big question that I'm trying to address is what is responsible for the muon G-2 discrepancy? Okay, so the muon is our favorite probe. It has a lot of cool properties and that make it particularly useful. One that I like to point out in our case is it has this sort of fortuitous lifetime of 2 microseconds, which allows us to create muon beams and manipulate them, but then have them decay quickly so we can do this experiment over and over again and get a lot of statistics. Relevant for the G-2, it's a spin half particle, and importantly, it encodes information about its spin in its decay to an electron. So the magnetic moment is proportional to the spin and some constants, including G, as Dominic explained. So that's the G in G-2. And Dominic did a nice job of explaining that the contributions that cause G to deviate from 2 come from these virtual particles. So when we think about what we want to do experimentally, effectively, we can think of a muon in a magnetic field as a gyroscope in a gravitational field. And when we look at all those Feynman diagrams, effectively, what's happening from the muon's perspective is that these particles are popping in and out of the vacuum. They are screening the B field experienced by the muon and ever so slightly changing the rate at which the muon processes in this field. And of course, Dominic pointed out that the particles we know about cause this deviation, but of course there may be other particles that are being created that are actually affecting the muon's precession that we don't know about yet. Okay, so the status of the anomaly before the Fermilab experiment, I try to capture here. So Dominic talked about the calculation where the sort of standard model QED particles and the standard model QCD particles get pushed through the machine, and the crank is turned, and we end up with a very precise prediction for the standard model value for G-2. This plot just shows the evolution of that over the last few decades. And this is in comparison to the value that was measured at Brookhaven about 15 years ago. in this green point. And it has led to this, at the time, 3.7 sigma discrepancy between the two. So it's natural to ask the question about what logical possibilities could explain this. Well, I think I've captured everything here in this box. So one possibility is the theory calculation is wrong. Another possibility is the experimental determination wrong. Perhaps the most interesting and motivating possibility is that new physics explains the gap, and that there might be some new particles that belong in the calculation that actually span the gap that we're not calculating yet. It's also possible that there's some combination of the above. These points can move around a little bit, and so we have to keep that in mind when we consider how to proceed. Okay, so one of the big questions I want to talk about today is, where can future experimental efforts help explain the muon g-2 discrepancy? And the three categories that I'm going to go into actually involve the theory calculation, the experimental number, and then these future experiments. So let's start a little bit with the theory. So Dominic explained that the dominant term comes from this sort of hadronic vacuum polarization. And this is just sort of this diagram here where you have this hadronic blob. And actually the calculation is driven by experimental input that relates terms like this in the calculation to observable processes like the one on the right. And you can see, if you sort of snip out this region of this diagram, you have a lepton interacting with a photon, producing some hadronic blob, which is exactly what you would see if you have an E plus E minus collider interacting and producing some hadrons. In fact, there are many different channels that could contribute to this, and this plot just sort of qualitatively gives you that impression. If you look at the actual contribution to the theory term, you're basically doing this integral where you have this R ratio, which is the cross-section to hadrons divided by the cross-section of E plus E minus to muons. And another really important feature in this calculation is that there's this 1 over S in the integral, which tells us that the low energy region of this plot is going to dominate. And so we would want to look at areas where the cross-section is high and the root S is low. And in fact, on the left-hand side here, we see that there are many detailed measurements that have led to this precise theory calculation. These are all, a variety of efforts, machines that have produced results. And this red region here is sort of the most important. It's low S and it's got a high cross-section. One of the interesting things from the experimental perspective is that these data from Chloe and Babar are in tension with each other. That's what's shown here in the green and yellow curves. The blue curve just kind of guides the eye to the region that we're looking at here. And so it's important to realize that when we make this when theory makes this dispersive calculation, that the overall combination uncertainty is affected by this by the tension in these results. Put a different way, if you calculate the contribution from this lowest order term from the input from the different machines, this basically you have to do something to account for the fact that the spread is a little bit too large. So where do we look next? Well, one of the really cool things is that many of these machines have more data already, are taking more data, and they're trying to push to improve to sub% precision on this contribution. So hopefully this will help clarify a little bit and give us some insights into what could be going on here to understand this discrepancy. Now, I do have one slide which is almost entirely not experimentally related here. I just want to reemphasize a point that Dominic made, that these new lattice calculations are in tension with the dispersive calculation that I just described. Many of the results are statistically limited, but this first precise result is definitely giving us some questions about what's going on. So as an experimentalist, I think it's really important for us to see how this story evolves. Will the other lattice calculations look similar with improved precision? Will there be a particular region or window that can be compared between these different results to basically get an understanding of why the results are different? And ultimately, if this holds up for this calculation technique, could this lattice result end up shifting the focus to an understanding of the discrepancy between a lattice and E plus E minus data, which would be a whole set of other new physics questions, what could be going on there? Fortunately, there's even one more approach that tries to come in with a perspective on what could be going on with this hadronic calculation. And that's this proposal to do a muon scattering on electron experiment at CERN. So I've taken some slides, and you can find where I've taken them from. This was from the Theory Initiative meeting this summer. The idea here is that you would make a very precise measurement of the shape of the differential cross-section of mu-e scattering. So you'd bring in sort of 160 GeV muon beam, scatter it off a target, and then very precisely track the trajectories of the muon and the electron. And this would allow, this measurement of the cross-section and some theory calculation would allow us to extract this alpha term, which is part of the way that one could calculate the hadronic vacuum polarization lowest order term. And so it'll be very interesting. This is an ambitious proposal. It'll be very interesting to see how it evolves. It involves detector techniques and very precise measurements with tracking. And they did some test beam studies in the last few years and are basically gearing up for when things come back on to do a test run in 2022. And ultimately, with about 3 years of running, they expect they could also get to sub% precision on this contribution. Okay, so I think that's all I want to say about the ways that experiment can inform theory. Let me briefly recap the G-2 experiment, the way it works, and what to look for there. So the way that I like to think about it is this equation, and I'll define the parameters in just a moment here. But a precision measurement of the muon's anomalous spin precession frequency in a well-measured magnetic field will tell us how the muons see the universe, right? What is popping in and out? What is causing this to move, to precess more quickly? So if we want to think about what this means experimentally, there's really 3 main steps that we need to do. We have to inject and store polarized muons. We have to measure the decay electrons from those muons to determine the muon's properties. And we have to map and track the magnetic fields so we know which field caused the muon to precess. Dominic already explained this very nicely. I just want to reiterate that when you start with an ensemble that's polarized here, the momentum vector just goes around and around with the cyclotron frequency proportional to B, but this spin vector evolves and picks up an extra term from the presence of a G-2. And actually experimentally, what we look at is the sort of beat frequency between these 2 spin and cyclotron frequencies. And that frequency we call omega A, and it's directly proportional to the strength of the field and the strength of G-2. Okay, so we've got these muons whipping around here, and when they decay, we measure those decay electrons to determine the muon's properties. We have 24 calorimeters around the inside of the ring. Those calorimeters are made of lead fluoride crystals, so the electrons come in and they give up their energy, which we digitize and watch here. Now, because these vectors, if you focus on this sort of middle panel here, because the spin vector and momentum vector are changing with respect to each other, the particles get a slightly different boost. And so if you look at the energy spectrum as a function of time, you'll see that you will actually get more counts above this threshold when the spins are aligned and fewer when they're anti-aligned. And if you count that and plot that in the left-hand side, you can actually see this beautiful wiggle plot that allows us to measure that beat frequency. And ultimately, this is what the data look like when we account for, when we've taken a lot of statistics in round 1. All right, the last part of the experiment that I'll tell you about is that we have to map and track the magnetic field. We use nuclear magnetic resonance here. So we have a bunch of samples, and then we determine the B field in terms of the precession frequency of the protons in those samples. We call that omega P. We actually use a variety of NMR technique, or a variety of NMR probes in the system. Some of them we put inside of a trolley, and we turn off the muon beam and actually map out what the field looks like directly where the muons usually live. Other probes live outside that region so that we can monitor the field during the times that the muon beam is on. And ultimately, all of these probes are made from real materials. And so we want to relate these to an absolute magnetometry standard. So we have some really carefully crafted cross-calibration probes of different geometries and different materials like water and helium-3 that allow us to calibrate all these probes so that we can get an absolute measurement of the magnetic field that a free particle would experience. Okay, and ultimately, our process generates a bunch of maps of the magnetic fields. And you can see as the trolley steps along, we can see changes in the magnetic field as a function of space. And we actually take these and map out this azimuthal distribution, and we weight it by the muon distribution so that we're really taking the B field that the muons experienced. So I mean, that's sort of the simple version of the experiment. And this is the equation that I showed you before. If you want to know A mu, you've got to measure the muon precession and you got to measure the magnetic field. Of course, in precision efforts, the things that you want to measure directly are not necessarily what you exactly measure. So the equation that we end up looking at is something more like this, where the red terms on the top relate to the muon precession and the blue terms on the bottom relate to the magnetic field. What the detectors actually see in terms of an oscillation is related to what the muon experiences, but it gets modified by beam dynamics effects and detector acceptance sort of issues. And very similarly, the magnetic field that the muon experiences is different from the one that we measure. We have to do these calibrations. We have to weight by muon distributions. And ultimately, a very important contribution comes from transient fields that are present during the muon storage period, but not during the trolley measurement that we have to do dedicated systematics to account for. So I'm not going to go into details about all these terms. That's a different talk. But I do want to give you a look forward here and what we can ask about future experimental improvements. So this is the error table from our run 1 results, and I really want to highlight these 3 red points here. That this experiment has a precision of 462 part per billion. I think this really builds confidence in the experimental results. Prior to our effort, it was unclear if maybe the experimental result Brookhaven was wrong. So now we have a statistically limited result. We have improvements that have been implemented already to help reduce the overall uncertainties to sort of 100 part per billion systematic. And as we keep crunching and taking more data, ultimately the statistics should also come down into about 100 part per billion. And although the technique is really the same as Brookhaven, most of the systems are new or even different in terms of the technology they use. So this isn't just we didn't just turn on the Brookhaven experiment again and take more data with it. There are lots of interesting innovations, which of course brings us to this plot, which you've seen. The dispersive calculation that was described is over here. And the Brookhaven measurement, which was statistically limited, you can see the statistical uncertainty, and the Fermilab experiment, which is statistically limited, are an excellent agreement, giving us confidence in that result. And the experimental average lives here now with a 4.2 standard deviation discrepancy, and a lot of room for improvement in the overall uncertainty. So another point to emphasize is that we're going to get more information about this in the short term. The data that we published in April was from run 1. There's an analysis of run 2 and 3 ongoing that we expect to see within a year. And we just finished a long run 4, and we're about to start a long run 5. So we really do want to see where the experimental result settles. I think it's very important to push this precision as far as we can, that now that we have this opportunity and this beautiful, beautiful data set, there is this uncertainty that we have with the theory number. And so we just want to put the best possible number we can on the map to give the most information to the community about what can be going on here. Okay, with the balance of the talk, I really want to turn to other experiments and try to relate them a little bit to the Muon G-2 discrepancy. Dominic laid the groundwork for a lot of this by describing various places that you could look for new physics. I'm just going to talk a little bit about experimental efforts that are underway. So the big question we're addressing here is, what if the discrepancy is real? Where could we look? Well, the community has done a tremendous job of trying to answer that question in the last 5 months. There's been a flurry of activity and nearly 300 citations as of this week of people referencing this and trying to describe things you can do or explain what's been going on. So Dominic also mentioned a bit the B anomalies. There are anomalies popping up in the flavor sector. Just earlier this year, there was this nice LHCb result. that probed this, or that did a precision measurement of this RK ratio, which is the ratio of B meson decays to muons divided by B meson decays to electrons. And it really gives us a hint that lepton flavor universality is violated. The decays preferentially seem to be going to electrons compared to muons. The tension here is about 3.1 sigma. And there are several other anomalies at the 2+ sigma level related to flavor distributions and branching ratios. The important caveat, I'm not trying to say this is the same physics as G-2 at all. There's an important caveat that it's challenging for theorists to construct the models that really accommodate all these anomalies in G-2. But it is interesting to think about the fact that these anomalies are popping up in the flavor sector repeatedly, and maybe the new physics is seeing muons in a different manner. And so it's natural to ask the question, where else can we look for effects of new physics to help us sort of resolve what's going on with these different anomalies? So one thing that people are very interested in doing is searching for muon Phyllic Dark bosons. So these are some dark matter particles that have a preference for attaching to muons. And I think it's important to note that you can easily explain the muon G-2 discrepancy in such a model, but it would need significant coupling strength in order to do that. And the consequence of that is that it could be produced in large production rates in muon beam experiments. And so this gets a little bit to the question that was asked earlier, that Dominic was mentioning. You could have a diagram such as this one. If diagrams like this exist, then you should be able to detect signatures where a muon would scatter off a target and emit one of these mediators. Now, the experimental design that you would pursue really depends on the manner in which the new particles decay. It could be that they decay invisibly to our detectors because they're decaying to dark matter, or they could decay in a manner that we can detect standard model particles. So just to give an idea of how something like this would work in the case of invisible decay, this is a schematic of a M³ proposal where you would actually track individual muons that would scatter on the target. And this new muon Phyllic particle would basically take away momentum undetected by your detector system. So then when you go to track the momentum of the outgoing muon in a magnetic field, you would see that there's some missing momentum there. And one of the really important things about experiments like this is you have to make sure that the missing momentum is not just hiding from you in some sort of standard model process or inefficiency in your detector to see, say, a radiative photon or something like that you end up missing. So this is one of the efforts. There is an effort at CERN in A64 that's gearing up for the LHC Run 3 that takes place at 160 GeV. And this proposal would be to do something like this at Fermilab in a much lower energy range and get some different systematic and detector effects because of the beam energy being a little bit different. It's also possible that the new particle could decay visibly, and so you end up then getting out either electron pairs or photons. And again, if you consider these two sort of beam lines, you could design different sort of experiments. One where you stop this muon beam into a target and produce these new particles, which would then manifest as sort of an anomalous energy deposition in an adjacent detector that you could measure directly, or you could degrade the beam and interact with the target and basically reduce the momentum of the particle and then not see the decay because it evades your detector as well. So these are just sort of some of the different ways that people are thinking about trying to detect the effects of this potential new physics. All right. So with the last few slides here in the talk, I just want to sort of broadly touch on the program that's ongoing. I've got some ongoing efforts in green and some proposals that are in blue. This is not an inclusive list, but I think it's important to think about other things that are going on in the field that could be related to the G-2 discrepancy, especially in this Snowmass era. So the first thing is to just touch on Muon G-2, right? We're going to have this improved precision of the Muon G-2 data. There's an effort ongoing in Japan to take a very cold mu plus beam and a much more compact tracking detector. It's a very challenging effort because of the beam challenges, but it would be very exciting to see a really different approach to determining G-2 experimentally, which I think could really provide value in the community. There's also other things you can do. There's a nice proposal to actually look at the data that has been collected by G-2 and see if there are some sort of long time variations in the G-2 signal. So actually looking at how the signal evolves over months or years could tell us a little bit about dark matter that could be potentially coupling there. And so this is a very interesting thing that we can do with data we already have. Lepton universality, we touched on this with B physics. It's important to improve the precision in the rates and the properties of B decays. Part of the Snowmass process, there's an LOI to do a similar effort with pion decay and study the ratio of pion decay to muons versus pion decay into electrons, which is an extremely precisely calculated quantity, and try to understand if there's lepton universality violations there. The charged lepton flavor violation program is very compelling, right? There's efforts all around the globe to look at muon decay to 3 electrons or muon conversion to electron in the presence of a nucleus. So these things are all happening. And in fact, if we get lucky and see mu to E conversion, a very compelling thing to do would be to improve the intensity of this this source and actually probe the operators driving muon to electron conversion, if that actually happens. And there's a lot of excitement in the community about trying to have a coherent charged lepton flavor violation program that's brought together leaders from all these different programs that are interested in studying multiple channels at the lab, at a lab. Oops. Okay, so I spent some time going through the sort of dark matter searches that are proposed and underway here. I think it's also important to, again, emphasize that we have some very large machines that are, would be extremely multi-purpose, like the high luminosity LHC. It would really extend our existing investment, and importantly, would probe part of the SUSY space into regions that could also explain the G-2 discrepancy. So it very much could be that this is eluding us at the moment, and we'll get there at the LHC eventually and find that, which would be very important. And there's also ambitious proposals and interests to do a muon collider. You can get clean lepton interactions, and you can get significant physics reach at modest energies owing to the mass of the muon. There are technical challenges associated with the creation, collection, and the acceleration of muons, but there's also sort of a proposed no-lose theorem that if the muon G-2 discrepancy is real, then this is guaranteed to discover new physics properties. Okay, so I come to the last question, which is really for you. Where do you think the solution to the muon G-2 discrepancy is lurking? I think Snowmass 22 is a great opportunity to present the physics arguments and develop community consensus to pursue these sort of interesting ideas. This is a great audience to be talking about these things with, because early career researchers are really pushing many of the efforts that we looked at today and defining the direction of the field. So this is really your opportunity to define what you think is important for the coming decade. So I won't go through all the details on the summary, but I hope I've given you some perspectives on different ways that experiment is going to help improve our theory understanding. It's going to improve our experimental results for G-2, and where there may be connections with future efforts. So I'd just like to thank you for your attention and welcome questions.
Fantastic. Thank you, Brendan. Thank you for the excellent overview, and thank you to both speakers for inviting and motivating early career researchers especially. So I invite questions now. Let's begin with questions for Brendan for a few minutes, and then we can open to general discussion. I remind you that we have reserved the event until 12:30 Central Time. Yeah, we have a first comment from Breeze, Brendan.
Yeah, sure. Thanks, Brees, for clarifying on this. So as I mentioned, this dark matter search here is something that can be done with the data we already have, and Brees has notified me we've gotten going on that. So this was a proposal that some folks in the theory community brought to us and said it would be possible to do, and so the communication between theory and the experiment motivated us to take on a new analysis that we were not previously looking at. So thanks for reminding me, Brees, that I should change the color on this one.
Yeah, we put a grad student on it, so he's working on it.
Great, thank you.
Any more questions or your opinions, your answer to Brendan's question on what might be causing the discrepancy? So Brendan, so to that question, what might be causing the discrepancy? I think I heard just yesterday a G-2 collaborator saying that there is 100% absolutely nothing missed in the experimental result. Is that your position, given the agreement between Brookhaven and the Feynman result?
I mean, no, not 100%. You have confidence in your result because you go through a very exhaustive procedure to try to understand all the different things that actually affect the properties that you measure. So we think we're very confident that we have correctly identified the corresponding uncertainties to go with each of the effects, and people have thought deeply about the various things that can be going on. But no, you can't with 100% certainty say you haven't missed something in the experiment, right? We're learning things all the time. And I think this is actually a really important opportunity to point out that when you do a precision measurement, it's my opinion that your intuition is really poor at the part per million or part per billion level, right? So you can have an intuition as to whether an effect can actually matter or not, but it's important to do the calculation and understand whether that effect matters or not. And so that's, it's one of the reasons it takes a long time, because you see things in the data that you don't quite understand, and you spend a long time trying to understand if this is an effect that matters, an effect that doesn't matter, and things like that. So I can say I'm extremely confident that we have captured our, the systematics that are lurking in the data. But one of the cool things with taking all this additional data that we have now is that we're going to improve our statistics. We're going to improve our statistics, and we're going to have more robust plots that allow us to really dig in and understand effects. It's usually the case when you improve the precision on something that you learn something new about what is going on that maybe doesn't affect things at the precision that you had here, but is important to understand as you improve your precision. So, okay, that's my take. I don't know if I answered it or not, but.
Yeah, you absolutely did. And apologies for the little provocative question, but it was something that I heard yesterday. So I know that the hand that was raised before wanted to ask a question about the lattice result. And Marshall, I see you have a question about the lattice result. Do you want to unmute and ask?
Well, sure. I was just wondering if, assume just for assumption that the lattice results eventually wind up agreeing with the experiment. What does that say about the standard model? Clearly, something is not understood still. What might that be? Because I mean, I'm assuming that the standard theory does not agree with that. So it's sort of, you haven't really gotten rid of the problem. You just sort of pushed it into a different direction or a different corner of parameter space.
Yeah, so I certainly invite Dominic. He's spoken quite a bit about this in the past, and I'd like to invite you to give your perspective.
Yeah, sure. It's not completely easy to answer this because there is not really the ready-made, let's say, new physics scenario which could explain this. But for sure, let me first say the following. Clearly, both the lattice gauge theory calculation and also the traditional dispersion relation calculation is based on first principles. They are based on rigorous quantum field theory principles, and therefore both of those kinds of calculations correspond to, let's say, rigorous standard model evaluations of the same quantity. Therefore, by construction, if the standard model is correct, they should give the same results. Of course, one of the two needs also experimental input, and then the interpretation of those experimental data might also have some uncertainty, but that is all factored in and taken into account in those error bars that you see in the plots. So therefore, really, all of those calculations should end up with the same result if the standard model is the correct theory. If, however, they end up in different places in the plot with, let's say, a strong significance, then you cannot easily say dispersion relations are wrong, or there is new physics in dispersion relations, or lattice QCD doesn't describe QCD correctly. Sure, lattice QCD by construction is closer to the standard model Lagrangian in a way. Therefore, if any of the two is really fundamentally the prediction of standard model theory, it would be the lattice one, while in the other calculation we have experimental data creeping in. So for example, there might be some new physics particles which are present at very low energy and which somehow modify our measurement of E plus E minus 2 hadrons by some interference effects or yeah, by some unknown mechanisms. And then, of course, they are part of the measured values which go into the standard model prediction based on dispersion relations. So what would be one way to explain such a discrepancy would be some new physics particles affecting the measurement or affecting the observables E plus E minus 2 hadrons. And quantitatively, it's not really easy to come up with scenarios which work really well. Therefore, there is not, let's say, a ready-made answer like, okay, it could be explained by supersymmetry, or it could be explained by Z prime particles, which are very light. It would be a more tricky kind of explanation, but it would be somehow new physics at very low energies, which would play a role in this E plus E minus 2 hadron measurements. And then we would really have to take seriously into account all possible effects which could play a role in those measurements. Again, of course, without violating agreement between standard model predictions and experiment elsewhere. And that is not easy. So it's a interesting.
It might be more useful then if you if they all three came up with different results, because that might be a clue.
It might give rise to very interesting new theoretical ideas, which could then be confirmed in such a way. Yes, clearly. So if the lattice ends up at very different places and then E plus E minus data and also the G minus 2 measurement, yes, then we have a hard job as theorists and as model builders, but a very interesting one too.
Great, thank you very much for that. Let me abuse my privilege and ask a follow-up. What do you see the status in the theory commitment about the commitment of different groups to perform cross checks on intermediate quantities and provide self-consistency checks? And how long do you see before we have some more insight on the theory side?
Yeah, it's a very important question. And of course, theorists are working very hard on this. In fact, today and yesterday, there was a workshop going on precisely focusing exactly on this. Basically, there were experts doing all these different calculations that you see on this plot here on the page. discussing, and there was a panel discussion. Unfortunately, because of this, also, I couldn't participate there, so I cannot tell you the very latest news, but there is a lot of progress and a lot of activity going on. However, the lattice QCD calculations are, as you usually know, not easy to do. They need huge computing resources, and therefore none of those calculations can be done on a very short time scale. But all these groups are continuing to work on this, and what is now happening in particular is to define intermediate results, intermediate quantities, which can be compared in a simpler way, so that we do not only need to calculate g-2 overall and then compare ultimate results, but many different intermediate quantities are being defined and have already been defined to some extent, which can be computed by everybody, and then one can find agreement or disagreement and disentangle why or what is the origin of various quantities disagreeing or agreeing, and in this way make progress and possibly also find pitfalls in the various lattice approaches. One should maybe also mention that these different lattice groups, they do not calculate using the same methods, because on the lattice QCD side, you have many detailed options of how to treat the lattice, how to treat fermions like quarks on the lattice, and pursuing all these different options creates very important cross-checks, because these calculations are, let's say, the first generation of lattice calculations of this new quantity. Therefore, all these different cross-checks are absolutely crucial. And therefore, each of those groups is contributing an important piece of information to this puzzle.
Thank you very much. We have another question on the dark matter. You showed a plot before. The question is, what is the dark matter mass window that Muon G-2 experiment will be sensitive to? Or I guess that the discrepancy points towards.
Right. So
yeah, okay,
go ahead.
sorry, yes.
Yeah, go
I
ahead
don't know
first,
which
Dominic.
plot is referred to, maybe Brendan's plot or my plot, I don't know.
I referenced an exclusion plot that Dominic showed, but yeah, feel free to, whoever wants can step up and answer the question.
Yeah, okay, I think, Dominic, you can probably say more. Can you guys see this plot I just dragged onto the screen?
Yes, yeah.
Okay, so this is one of example sort of from the missing momentum searches, trying to show what their sensitivity would be in different scenarios. I think it depends. I mean, Dominic can say more, but it depends on the specific physics model. But for these models, they're talking about MEV scale up to maybe twice the muon mass scale that they would be sensitive to. In the case of the things that G-2 could already look in the data that we have, you're talking about really ultralight. You're talking about really ultralight particles. I think I know the.
Yeah, I can speak to that a little bit.
I think it's. Yeah, go ahead, Bruce. No.
Yeah, roughly 10 to the minus 12, 10 to the minus 22 EV. Exactly what the range is. That's sort of what we're working on now. Exactly what we'll be sensitive to. But yeah. That's the right plot there.
Yeah, so it really depends if you're talking about looking for modulations in the G-2 signal on the sort of hourly level, which would be something, like 10 to the minus 12, or over the course of the entire experiment, which would be, 10 to the minus 21, I believe. So, and these slides were borrowed from recent workshops here. These are not mine. But Dominic, do you want to address other dark matter ranges?
Just to add to that, I don't know, my window here seems to be frozen, whether you can hear me, but anyway, I will go on. So there are, of course, other dark matter models, which are not only related to very light new particles, but as I mentioned, supersymmetry is a primary motivated candidate for physics beyond the standard model. It contains dark matter candidates as well, and those would have masses of around 100, 200 GeV, so in the energy range of interest for the LHC and other high energy colliders. And there is a variety of models of that kind, also without supersymmetry. And so they are also able to explain G-2. But it cannot be much higher than a few hundred GeV. This is typically the maximum mass reach that you have, or the typical maximum mass that appears in new physics scenarios, which can explain G-2 and dark matter.
Great, thank you very much for that very complete question, everyone.
Can I quickly just ask one question?
Yes, please. Sure.
Regarding the last comment from Dominic about this SUSY dark matter particles. So I wonder that if we are looking for those mass range, and will that be detectable with this oscillation experiment, or you have to do it completely differently?
They would be detectable at the LHC, not directly, but indirectly by producing other particles which then decay into those dark matter particles. So these particles and the explanations of G-2 always work by having several new physics particles, some of them a little bit heavier, some of them a little bit lighter, and the lightest of them would be a candidate for dark matter. And then at the Large Hadron Collider, you can produce the heavier one, which decays into the light one, which is a dark matter candidate, but you would see in the detectors of the LHC the decay products, standard model particles which are produced in those decays. For instance, in the case of supersymmetry, you would produce the superpartner of the muon, which decays into the muon itself, plus a dark matter particle, and the detectors would measure muons plus missing energy, and so the LHC is sensitive to that, and in that way you can test such models for dark matter plus G-2 like SUSY.
Thank you.
Thank you very much for that. Any more questions? Would you like to unmute for the question in the chat?
Hello, can you hear me?
Yes.
So I'm kind of new to this, but from my previous knowledge of particle physics experiments and such as like accelerators, from your Feynman diagram, would your photon emitted either by the muon or, emitted by the muon, either absorbed by the new particle, be observable at all? Or is it worth looking at?
In general, yes. Yeah, depends on the specific model you're talking about, whether you have supersymmetric particles or these Z prime particles or very light particles. So generally speaking, probably the best distinction is whether the new physics is of the order of GeV or below, or many GeV. If your new physics particles have masses of the order of many GeV, hundreds of GeV, then of course high energy colliders like the LHC are very good places to look for those particles, and the detectors are built to be sensitive to particles if they are at least leptons or other particles which can be easily detected. However, for the very light new particles, you need specific experiments which are specifically designed to look for those mass ranges. And the example by Breeze and Brendan just now was, of course, very interesting. This oscillation or this time dependence of the G-2 value itself would be sensitive to dark matter particles with masses of what, 10 to the minus 22 electron volts. So extremely small mass range and a very specific kind of measurement. So it depends on this. But particles with masses of tens or hundreds of GeV are typically detectable at the LHC. However, of course, there are ways to hide them, and in that way you can also understand that supersymmetry, even though the LHC has excluded large parts of the parameter space relevant for supersymmetry, there are still, let's say, wide open regions which are not excluded by the LHC, but which allow to explain G-2 and dark matter also in supersymmetry.
Thank you very much, Dominic, for this response. So we invited early career people to participate in these experiments, and Brendan, you showed a lot of experimental efforts that are coming up. And you know, we all want to have results and to look at these results and kind of push human knowledge further and know how have a find physics beyond the standard model, have a fundamental theory of the universe. But just to make the point, Brendan, you started working as a very early career person, and you had to work on this for a decade or about, doing very grueling work before you can get to the point to present this very important result. So any thoughts on that kind of duality of doing physics work as an early career person?
Well, I think it's not ideal, the ideal way, right? I mean, typical career trajectories, you'd like to, have some highlight and presentation and not wait a decade to do that. So I think that's a sort of an unfortunate side effect of some of these large efforts. However, I think there are lots of opportunities to think about smaller scale efforts that are complementary to other things that you're working on. So getting involved and listening to the various things that are going on and finding the similarities in different techniques can allow you to do two things that have different timescales with very similar infrastructure. So I've been very impressed by seeing the collaboration both between the theory and the experimental community on ways to maximize output from existing efforts, or for ways to slightly modify existing beamlines to go after broader physics reach, or build on existing detector designs. So I think those are the sort of things that are important for multiple reasons. One is to maintain your own stimulation and variety. I think that if you focus on one question, one problem for 2 decades, I think that can be very grueling and difficult. And so having some variety there is really rejuvenating and important. I mean, you see this a lot in many professions where people sort of define a time period where they're focusing on something and they want to, be re-energized by moving on to the next sort of topic. I think that is important. So yeah, I'm again not sure if I directly answered your questions, but I think this next year period, right, where we've got all these workshops, starting with Snowmass Day next week, and then all these different workshops leading to the sort of the big community sharing the different things that are interesting, really is a very stimulating prime opportunity for all of us in the community to, be talking about what's important and looking for those commonalities and building new collaborations and efforts to get on the roadmap, so that you have the thing that you're working on and the curiosities that you're thinking about that can manifest if there's the right opportunity. And I know I've rambled a bit, but I think opportunity is the other thing. You don't always, I mean, there's a lot of politics that goes into these very, very large machines, and sometimes even the smaller efforts. But sometimes you just get an opportunity to run with something, and if you've got that great idea there and the community buy-in, it's a great chance to do it.
Thank you for the great response on a very general question. So one last question for both of you to address, I guess, and we might go a few minutes over on an already long period. Just to address the context of no physics beyond the standard model coming out of the LHC, and now some very significant discrepancies from precision measurements in g-2 and B meson decays. So Dominic, within that context, how has your perception of naturalness in model building and using minimal extra fields, how has that evolved? And Brendan, perhaps how do you see the rare and precision frontier efforts within that context? And I apologize again for the very broad questions, but
this question is really super broad. Thanks for asking it, but it's not easy to answer. So of course I thought a lot about this question of naturality or naturalness after the LHC results, and I think it's too early to really come to a conclusive answer because let's say, first of all, many ideas that we had before the startup of the LHC, like simple ways of supersymmetry, simple realizations of models which have extended Higgs sectors, which explain the mass of the Higgs boson and the scale of electroweak symmetry breaking, all these ideas where we thought the LHC would not only discover the Higgs, but immediately it would also discover some mechanism which explains why the Higgs is there, why the Higgs potential has the form that we need to explain electroweak symmetry breaking. So this has not happened yet. And but it doesn't mean that all those ideas are incorrect. As I said, supersymmetry is this example. It was a very good explanation of the G-2 result after the Brookhaven measurement. And it still is a very good, one of the most attractive and most natural or simple explanations of the current G-2 result as well, despite the LHC having ruled out a large part of the SUSY parameter space. So still now we can explain dark matter and G-2 nicely within supersymmetry with supersymmetric particles in the ballpark of 300, 400, 500 GeV without conflict to LHC data. So that tells me that it is much too early to say all of those ideas that we had before the LHC are now excluded. We cannot have supersymmetry at the TeV scale. All of this was wrong. We have to give up on our ideas of natural electroweak symmetry breaking. So we cannot draw this conclusion at this point in time. So, it might take quite a number of years until these explanations of G-2 via supersymmetry or alternative scenarios of TeV scale physics like leptoquarks are completely excluded. I think it will not happen in the next 5 to 10 years because the parameter space is wide open and there are regions where we can explain G-2 which will not be covered by the LHC anytime soon. And therefore, I'm not prepared to give up on the idea of naturalness. However, it clearly has been challenged, and therefore we need to be very, very open-minded towards completely new directions, which have maybe nothing to do with TeV scale new physics, which involve completely different explanations of dark matter, not by WIMPs, but by, for example, 10 to the minus 20 electron volt dark matter particles, or by dark matter particles at the MeV energy scale. So this becomes, of course, much more of a hot topic in the theory community and in the model building community. And generally speaking, this fact that we see anomalies in the flavor sector connected to muons is extremely interesting. And this second fact that it's not easy to explain B physics and G-2 simultaneously with the same mechanism makes it even more interesting. And therefore, it shows that we need this complementarity between all of those different experiments. It's also not correct to draw the conclusion that we don't need the LHC, we only need flavor experiments, because of course the LHC and other high energy colliders are extremely important to give us constraints on the parameter space by which we explain those flavor phenomena. So we clearly need a multifold effort on all these frontiers, high energy colliders, and also precision experiments, and also flavor violating experiments to make progress. And so for me right now, it's a phase where I don't know what the right way to think about new physics is, but that as a phenomenologist, we need to be open-minded anyway, and or we should be. And so I'm maybe more open-minded than I ever was in the past. And so this is also my recommendation to everybody else, to remain open-minded towards all these different diverse ideas for physics beyond the standard model. So that would be my answer to your question.
Excellent. Thank you very much. Brenton, would you like to take it on too?
Yeah, I just want to build a little bit on what Dominic said. And I think when you don't see what you expect, you might initially be disappointed, but it really is an opportunity to stimulate different ways of thinking. And so I think it's important when you have null results, when you have interesting anomalies. It's all part of the puzzle, right? The new models have to accommodate the things that you're seeing in multiple sectors. So the more information we can get, the more we can kind of steer our thinking. And I think the last thing that Dominic was saying about being even more open-minded at this moment, I think, really speaks to the spirit of what's being done in Snowmass here, where people are trying to put everything on the table and think about all the different things, communicate it broadly, build these collaborations. And, I think there are going to be some really strong ideas that emerge that'll help, propel us to search in different places, because we have eight years more information than the last time Snowmass was ongoing. So, yeah, so I pretty much agree, and I'm excited to see the ideas that are generated now. So.
Fantastic. Yeah, thank you both very much. Apologies again for the very general questions, but I think, yeah, it generated some excellent comments from you. Thank you very much for this fantastic talk to our speakers, Dominic and Brendan. And thank you very much to everyone for attending. We went pretty long on this, but I think we had some great discussion. So thank you very much, everyone.
Thanks a lot for the invitation.
Thanks a lot as well.
And yeah, I'll see you next week for Snowmass Day, next Friday. Thank you, everyone. Have a very good Friday and a good weekend.
Bye-bye.